All right, hello everyone. This is going to be a lecture on Objective 14, which is precipitation equilibrium. Uh, to give you another reference, this is pretty much the last part of Chapter 18 from the textbook that we're going to talk about. Uh, Funny enough, when I was applying for my position here at Adelphi, this is the lecture that I had to give as a demonstration for me to get the job. I had to modify the lecture since then. Didn't think it was all that great, but obviously now with a year's worth of teaching experience, uh, you know, obviously made some changes. But I'm gonna use the framework of the slides that I made when I was applying here. Not that that's important to you guys, just wanted to uh, mention that. But yeah, we're going to wrap up pretty much all of chapter 18, right? This is objective 14. Let's talk about precipitation equilibrium and what that even means. So, uh, pretty much this is talking about the solubility of ionic compounds. Okay, so we're going to talk about solubility of ionic compounds, and this is a little bit of a flashback for you guys because in Gen Chem 1 you learned that ionic compounds, just so you know, and just a little bit of a recap on what ionic compounds are. An ionic compound is made of a metal, which is usually positively charged, right? And a nonmetal, which is usually negatively charged, right? When you have a metal and a nonmetal, right, a positive and a negatively charged species, you can form an ionic compound, right? But the criteria is that it has to be a metal and a nonmetal. The only other exception to that is when you have ammonium NH4 plus, that's a polyatomic ion. That's the only time you really see a positively charged species that is not a metal, but it's still positive. And then, the counter ion could usually be a non-metal species or a polyatomic ion that's negatively charged, all of which are made of nonmetals. But that's what an ionic compound is. And the question is, when you put an ionic compound in water, if I put an ionic compound in water, is it going to solubilize? Is it going to dissolve, right? Or is the plus and the minus going to break apart, right, is the question. And in Gen Chem 1, you learned that things are either soluble, meaning that if you have an ionic compound in water, it's going to go more to the right and not much to the left, right? So if it goes more towards the right, that means the plus and the minus, the metal and the non-metal, break up and they fully dissociate in solution. And I have a graphic here. Here's just a beaker of water with your ionic compound, and you can see the positive and the negative ions are spread out pretty nicely, right? You also learned that ionic compounds could be insoluble, meaning that if you put an ionic compound in water, the plus and the minus, the metal and the non-metal, are not going to want to separate from each other, and they're just going to want to stick around in solution and not break up into their ions. And this is something that's called insoluble, right? So you've learned all about this. And how you knew whether an ionic compound was soluble or insoluble. Remember the solubility rules, right? This is a table showing you the solubility rules. I made you guys memorize this back in the day, and I hate asking you to memorize anything. But this was just one of those tables where you had to know which positive ions, when they're paired with a negative, is it going to be soluble or insoluble? Likewise, if you see compounds, with ions that are negatively charged, if they pair up with something positive, is it going to be soluble or insoluble? So what this objective really focuses on is that this insoluble concept is actually an oversimplification. It's not like ionic compounds don't dissolve at all. Really, this doesn't even exist, right? Like, it's not like something's completely insoluble, right? In reality, some of the ionic compound in water will dissolve, even if it's just a tiny amount, right? And what we talk about really is something that's partially soluble, right? So if you look at your solubility rules and you figure out that something's actually insoluble, right? It doesn't break up. In reality, it does break up, but probably very, 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 very little of this will break up into its counterparts. And we classify how much they break up with an equilibrium constant value, right? Remember what an equilibrium constant is? When you write the expression, that constant is telling you the amount of products divided by the amount of reactants. And in this case, this is the product side, your positive and your negative species, divided by your ionic compound. But remember, ionic compounds don't belong, solids. Right? Ionic compounds are solids when they're not in water. They don't belong in an equilibrium expression. Remember, we said solids don't belong in an equilibrium expression. But what I'm really getting at here is that the value of the equilibrium constant tells you how much something goes towards the right? Remember, we said if we have a really large K, if we have a really large constant, what that means is that the reaction wants to go to the right, favoring the products. If we have a really small K, then it's favoring the reactants, right? Or really just the species on the left side of an equation. So when we say something's partially soluble, what we really mean is that, the equilibrium is barely going to the right? This ionic compound is barely becoming products, and that, therefore, the K for this solubility of an ionic compound, that constant is going to be really small, okay? But in reality, this is what happens. And look at this diagram. So this is an oversimplification. This actually doesn't really even happen, because some of the ionic compound will break up into its constituent ions. It will. And this is a better depiction of what actually is happening, right? Imagine this is your ionic compound, right? Positives paired up with negatives, and this is in water. Some of the positive and some of the negative will dissociate, will go into the solution, right? I just showed one of them here, but that's really what's happening. Right? So I'm just going to write this out, that this is an oversimplification. I'm going to say, let me go back to pointer options. I'm going to say that this is an oversimplification. Simplification. This is what's actually happening. Right? And we're going to look at a lot of examples where we see an ionic compound and how much of it actually, how much of that solid ionic compound is going to break up into its ions, right? To what degree does each ionic compound do that, right? Every ionic compound has a unique solubility, right? A unique K, a unique constant, right? How much of it is going to go towards the right, towards products. That's really what we're going to look at here, okay? All right, let's go back to my laser pointer over here. There we go. So let's dive into what we really mean by solubility equilibrium. Okay, so here's your generic reaction, quote unquote. This isn't even really a reaction. This is just showing you how an ionic compound breaks up into its positive and negative counterparts in water. And the degree to which this is happening, we describe it using something called KSP. KSP is a solubility product constant, right? It's just an equilibrium constant for a solution representing, basically just for a chemical solution representing the dissolution of an ionic compound, right? So you can think of it kind of like a reaction, but it's, I wouldn't say it's a reaction. I would just say that it's an ionic compound breaking up. And, You guys know, like I said, that solids don't belong in an equilibrium expression, right? So the KSP, the solubility product constant, is equal to the concentrations of your positive ion times the concentration of your negative ion. And you guys remember that anything in brackets means moles over liter, right? It's just molarity. But in this particular case, when we're talking about brackets for stuff that's, describing the dissolution of an ionic compound, these brackets really mean molar solubility, right? So what that's telling you is the solubility of, let's say, a positive or negative species in moles per liter, right? So any number that's in here is just describing the molar solubility of that ion in solution, okay? And here's just a couple of examples. Notice I use some of the same color coding. The dissolution of copper 1 bromide, for example. Here's copper 1 bromide. It's a solid, and the question is, how much does it break up? And obviously, if it does break up, it's going to be in copper plus and Br minus. And if I wanted to write the KSP expression for this, it would be KSP equals the concentration of my copper plus 1 times the concentration of my Br minus 1. And as I said, these solids do not belong in an equilibrium expression, right? Because they're solids. Remember, solids don't change concentration, right? The concentration of a solid is always going to be constant. We don't put it in the expression, right? The concentration of a solid is based on its density, right? And the density of a solid doesn't really ever change, right? It's always going to be the same. So we don't put that in the expression. And this is what the KSP for this dissolution of an ionic compound would look like. And check this out. This KSP is 6.3 times 10 to the negative 9, right? Really small number, right? What this number is telling you is this is barely going to the right, right? In reality, this is wants to stay solid and barely become the positive and negative parts in solution. Right? The smaller this number is, the smaller the KSP is, the less it's going to go towards the right, towards the products, which are just, the ions. Here's another example where you have the dissolution of calcium fluoride, right? Calcium fluoride is CaF2. And when you show the dissolution of this, you're going to have 1 calcium, 2 plus ion, and 2 F minus ions. Why is there 2 over here? Because there was 2 of these on the left, right? Calcium is a group 2 metal, has a positive 2 charge. Fluorine is a group 7. So fluoride gets a negative 1 charge. And there's going to be a coefficient of 2 in front of it because there was a subscript of 2 in the ionic compound. You guys need to remember how to write out dissolution equations, right? So how do you figure out how this breaks up into these? You need to be familiar with that at this point. And if you're not, I would strongly recommend to practice writing out the dissolution of ionic compounds, right? Figuring out what a solid ionic compound looks like when it breaks up into its positive and negative counterparts. Right now, it might seem obvious how this works, and it's really not that hard, but you should get used to being able to do this comfortably at this point. So the KSP for this is going to be the concentration of calcium 2 plus times the concentration of my F minus squared, right? This makes sense. If I'm trying to write an equilibrium constant expression for this, particularly the solubility product constant expression, the coefficient turns into an exponent, right? Just like all the equilibrium stuff we've seen before, right? Same exact idea. And in this case, the KSP for this solid turns out to be 1.5 times 10 to the negative 10, right? So even smaller equilibrium constant, and you would probably guess that, it means that because this is smaller than, let's say, this, you would think that this is actually less soluble or less willing to break up than something like this. But we're going to look at and see how that's actually not true. You can't always define how soluble something is, how much an ionic compound is willing to dissociate and break up. it's not always going to be based on the relative KSP values, right? We can't relate these and be like, oh yeah, this is more soluble than this because this KSP is larger than this one, right? We can't always make that assumption, and we're going to look at examples where, uh, you know, why we can't actually make that assumption. We're going to look at that. Trying to go to the next slide here. Let's see. All right, check this out. We got a table of ionic compounds and their KSPs. So it's not like you have to memorize this, right? Don't memorize this table, please. These would be given to you, right? So if you're given a problem that, has iron 2 carbonate, for example, and they ask you to solve a problem, a solubility product constant problem with this, they're going to give you the KSP. It's either that or they're going to give you enough information to solve for the KSP. And we're going to look at examples of this. But bottom line is that what I really want you to pay attention to with this table is that every single ionic compound has their unique KSP value, right? Their own constant. It's just telling you, giving you information about the degree to which these ionic compounds will dissociate and dissolve into their positive and negative counterparts. That's pretty much all this table is telling you. And like I said, don't waste your time memorizing this. This is just showing you that all these ionic compounds have a unique KSP. So here's a practice problem where, imagine there was a problem that asks you to calculate the molar solubility of AgCl, which is silver chloride in pure water. How would you go about doing that? Well, you guys understand that AgCl, if you look at your solubility rules, is actually deemed insoluble. But we just said that in reality, nothing's ever insoluble. It actually is soluble to some degree, right? This will dissolve a little bit. And how much? Well, here's your KSP. Look how small that KSP is. What this is telling you is that this is barely going to the right. It's not that it's completely insoluble. Some of it will break up into its positive and negative counterparts, just very little of it. But the question is how much, right? This is a constant that's telling you the degree to which it's going to the right. But the question is, what are the concentrations of silver and chloride when you start to dissolve it in water? That's the question. And the way we figure that out, whenever we know that two things that are together originally, and then you're thinking, well, how much do they break up? Remember we talked about strong acids and strong bases, and we said that because they're strong, they, completely break up into their counterparts. But in this case, we have an ionic compound where it doesn't completely break up, right? What other kinds of things don't completely break up into their counterparts? Remember we talked about weak acids and weak bases, how those also don't break up into their counterparts, right? They break up a very little amount, and similar idea, right? These ionic compounds that are deemed insoluble do break up a little bit, but how much? And we know it's not going all the way to the right, so we need to figure out how much of it breaks up. The way we do that is we set up an ice table, right? Because an ice table is going to tell us the change, right? You're starting initially at zero concentration of each of these positive and negative ions. But then at some point, some of this will dissolve into the positive and negative counterparts. And the question is how much? It's defined by this X value, right? So your equilibrium concentrations are going to be X and X. And now, just like all the other ice table problems you've done in the past, you are going to now take your equilibrium expression. In this case, it's KSP equals the concentration of silver plus times the concentration of Cl minus. You plug in your equilibrium, concentration variables, which is just X and X. So KSP is equal to X squared. And we know what KSP is. It would be given to you in the problem to be able to solve for X. And there it is. We solve for X. It's 1.33 times 10 to the negative 5. What this is telling me is the molar solubility of silver chloride. Right? So what this is telling you is this is the amount of silver and chloride that is going to solubilize in solution. This is the amount that's going to dissociate in solution. Okay, obviously there's a molarity in front of this, right? So here it is. The concentration of silver and chloride, because they're a 1-to-1 ratio, or they're going to be the same amount, right? Which is this 1.33 10 to the negative 5 molar. Okay? All right. Here's another practice problem. Same idea. It says calculate the molar solubility of lead chloride. So with lead chloride, realize that, it's the same idea. But remember what I said, you really need to get used to figuring out how to break these up, right? Notice right now it's PbCl, lead chloride 2, right? PbCl2. So how does this break up? Well, we know that Cl is a group 7 ion, right? So it's always going to get a -1, right? Cl minus 1, and there's 2 of them, right? So this subscript becomes a coefficient of 2. And we know that we won't need to balance our charges out, right? So if each Cl is worth -1, but we have 2 of them, this entire thing is worth -2, right? And obviously the lead, the Pb, has to be a +2 to be able to balance out the -2, right? We need to be able to neutralize all that charge, right? Because the charge on the left is neutral, 0, right? Right? This has a charge of 0, this total thing. And remember that the charge on the left has to equal the charge on the right, right? Remember, this is going back to Gen Chem 1. This is really important to understand this, because if you don't get this right, like the equation part of this, of how this actually dissolves, right? How it breaks up, you're going to get your answer wrong, right? All of your work is going to be wrong. So it's very important that you know how to break this up. And really the way I would think of it is I would always look at the piece, like the ion that I know what the charge is, and then I can figure out the charge of the other one, right? Pb, lead, is a transition metal. So transition metals, we don't know what the charges could be for transition metals, because that's why they call them transition metals. They can transition oxidation states, right? Meaning they can transition going from like +2 to maybe something else, right? But in this particular case, it's 2+, right? Or +2. So this is important because now you know that there's 2 chloride ions for every 1 lead ion, right? And when you're writing out your ice table for this, notice these are not a 1-to-1 ratio anymore. It's 1-to-2. So your change is now going to be +x and +2x, right? For whatever certain amount you change of this is going to change 2 times more, right? Because for every 1 of these, you have 2 of these. So +x +2x, and now your equilibrium expressions are x and 2x. And now we're given the KSP, would be given in the problem, and when we solve for this, now we got our KSP expression. Notice the 2 goes from a coefficient to an exponent in our expression. This is classic. And now we got KSP equals, we're going to plug in our equilibrium concentrations, right? X and 2x squared now. And you guys remember that 2x squared is 4x squared, right? Because the squared distributes over both the 2 and the x, right? So 2 squared is 4, x squared is x squared. So we got 4x squared times x, right? From this, which is now going to be 4x cubed, right? So notice that in the last problem, we had KSP equals x squared. Now it's a situation where we got KSP equals 4x cubed. And all of this is because this is a 1-to-2 ratio of ions, right? Notice how much this dramatically changes when you all of a sudden had a 1-to-2 ratio. And now if you solve for x, well, what's the easiest way to do that? You just divide by 4 first, and then you can take the cube root to then be able to solve for x. And there we have it. There's your molar solubility for this dissociation of lead chloride, right? So you can imagine that your lead concentration is going to be just x, right? And then your Cl minus concentration is going to be 2 times this number. So we're describing the molar solubility of each of these ions when they dissolve in water. Hopefully this makes sense. And, you know, as always, if you have any questions on this, but this is pretty much the gist of KSP, right? And we're going to start to get into some details of, you know, how we can manipulate this sort of procedure, this process to get other kinds of information about solubility of ionic compounds. All right, here's a practice problem for you guys. So you can try this on your own. Calculate the molar solubility of iron hydroxide, FeOH2, in pure water. And here's the KSP for it. As always, you know, in lecture, I do a problem and then I have you guys try a problem on your own. So you can give that a shot. I do have the answer right over here. So you can compare your answer once you're done. Okay. All right, here's another practice problem. So now imagine they give you the molar solubility of an ionic compound. They said the molar solubility of silver 2 sulfate in pure water is 1.4 times 10 to the negative 2. So this is silver sulfate, and they gave you the molar solubility. Calculate KSP. Okay, well, if you want to calculate KSP, same process, right? The first thing you got to do is figure out how does this break up into its plus and minus counterparts. And you know that silver is a +1. It usually is always +1. That's one of the exceptions of you know, remember in Gen Chem 1 I asked you guys to memorize which ions have a, you know, pretty consistent oxidation state. Silver is one of them. It's always +1 generally. But if you, let's say you didn't know that, how would you figure out how this dissolves? Well, you know SO4 is a polyatomic ion. Hopefully you know this. You also had to memorize polyatomic ions. I know that's pretty annoying. There's so many things to memorize, but polyatomic ions, make sure you know them, guys, because that's going to come up anywhere in Gen Chem, you know. Gen Chem 1 and 2, it carries through. So make sure you study your polyatomic ions, and particularly the charge of a polyatomic ion. So for SO4, you should know that that's always going to be a -2, which means that if I have 2 silver ions, I'm going to have 2 Ag, but what's going to be the charge? Well, if you didn't know it was +1, if you know SO4 is -2, that means this entire thing has to be a total of +2, right, to balance out the charge, right, because the left side's neutral, which means the right side has to be neutral. Remember, the charge on the left side has to equal the charge on the right side of the equation. So the only way you can get a +2 is if each silver is worth +1, right? Great, so now we know what this looks like, how it breaks up. We set up our ice table. Initially, we have none of these ions. Imagine initially none of this broke up, but now the change is going to describe how much of it breaks up, right? So we got +2x and +x because it's a 2-to-1 ratio between these. And therefore, our equilibrium concentrations are 2x and x. Now we write out our KSP expression. It's going to be concentration of silver squared, right? Because there's a coefficient of 2, becomes an exponent, times the concentration of SO4 2-. We plug in our equilibrium expressions, right? And we get that KSP is again 4x cubed, right? Makes sense because 2x squared is 4x squared, and then times x is 4x cubed. We do the same kind of math we did in the previous slide, and we solve for, well, actually, we don't need to solve for x, excuse me. Right? Because we don't need to solve for x because they didn't give you the KSP. They want you to calculate the KSP. They actually gave you the molar solubility, which is x. Right? Remember, the molar solubility is always going to be whatever x is. So you can plug this in, and notice that's what I did. The KSP is equal to 4 times x cubed, and the x is 1.4 10 to the negative 2. We plug that in, and we get our KSP for silver sulfate. And this should match on whatever it's listed on the table. Not that that would be given to you or anything, but you know, now you know how to calculate KSP when you're given the molar solubility. And here's a practice problem. So you guys are going to give this a shot, right? The molar solubility of now silver bromide, AgBr, in pure water is 7.3 10 to the negative 7 molar. Calculate KSP. Same process. I want you to give this a shot. I do have the answer right over here. This is a lot much more simple of a problem because this is a 1-to-1 ratio of silver and bromide, right? So it's just going to be X and X. Okay, so remember what I said before, that you can't just look at the KSP between two ionic compounds and then be like, oh, this one is going to be more soluble than this because, you know, this has a larger KSP than that, right? You can't really say that. And there's a really good reason, because how many ions does this produce when it breaks up? Let's think about it. Mg and OH2. Remember when I had you guys calculate the Van Hoff factor I? I basically asked you, like, how many ions do you have when an ionic compound breaks up? Like, how many moles of ions do you actually make when you break up an ionic compound? That's kind of the idea here, right? Is in this case, MgOH2 breaks up into 3 parts, right? 3 ions. You get an Mg ion, right? Mg2 plus, and 2 OH minus ions for a total of 3 ions. And this is important because when you do your ice table and you figure out what your molar solubility is, check this out. Notice what's happening here. Notice that the solubility ends up being larger in this case for the one that has a smaller KSP than this, right? This is a smaller number than this, but yet look at the KSPs, right? This is a larger KSP, but a smaller solubility. And this is a larger KSP relative to this. Excuse me, yeah, I think I just said that this is a smaller KSP relative to this, but this is a larger solubility, right? So it's not just dependent on the KSPs. We can't just look at the KSPs and say which one's more soluble than the other based on the KSPs. Right, the solubility is going to depend. The solubility of an ionic compound is going to depend on the molar solubility. Right, this is the number that actually tells you which is more soluble, and that makes sense, right? Because if this number is larger, what that's telling you is that there's more of the ions concentration-wise in solution, which is effectively telling you, you know, how many ions you have in solution, right? So these are the numbers that tell you what's more soluble. All right, look at another example over here. In this case, you actually can use the KSPs to determine which one's more soluble. And the reason for that is because we just said MgOH2 produces 3 ions in solution, right? Calcium fluoride, CaF2, also produces 3 ions in solution. Right? So you got calcium 2 plus and 2 F minuses. That's also going to produce 3 ions. So each of these ionic compounds produce 3 ions, right? 3 moles of ions. And when you calculate your X, if you set up your ice tables for these, what you'll realize is that you'll get your solubilities, but you can actually compare the relative solubilities between these two. And you can compare their KSPs in this case because these both produce the exact same number of ions. We're going to look at some math problems that are related to this concept to actually show you what I'm really talking about. Right now, I'm just telling you conceptually that if you have 2 ionic compounds that produce the same amount of ions in solution, and you're trying to figure out which one's more soluble than the other, right? Which one breaks up more into its ions. When the ionic compounds you're comparing produce the same number of ions, the same moles of ions, you can compare their KSPs. But notice in this case, these produce different amounts of ions, and you can't just easily compare their KSPs, right? Because you know that if this is producing 3 ions, but let's say iron carbonate, FeCO3, right? Fe is 1 ion, CO3 is another, that's a polyatomic ion. These produce 2 ions for every 1 mole of iron carbonate, and this produces 3. If they produce a different amount of ions, you can't compare their KSPs to determine the solubility. You have to look at the X, in your ice table, the molar solubility value, to determine which one's more soluble. Okay? But when they produce the same number of ions, in this case, when you're comparing these two, these both produce 3 ions for every 1 mole of, the ionic compound. And if they produce the same number of ions, in that case, you can compare their KSPs. And we're going to look more on why that makes sense mathematically. But I just wrote the generic statement that the relative solubilities can be predicted by comparing KSP values only for salts meaning ionic compounds, right? Metal, non-metal, that produce the same total number of ions. And the only comparison here we can make with KSPs is right over here, okay? So let's look at the math a little bit and try to make sense of what I just said, right? Why is it that you can look at, a compound that produces 3 ions and another one that produces 2, and you can't look at their KSPs? Let's take a look mathematically why we can't just easily compare KSPs all the time to determine how soluble something is. Well, just to kind of recap, a KSP is just one value, right? It's a constant at a given temperature, versus the solubility, the molar solubility, could be different values in different kinds of solutions. Let's take a look. So imagine I have this example where I have copper sulfide breaking up into copper 2 plus and S2 minus. And now imagine I have another example where I still have a sulfide, but I have Ag2S, silver sulfide. And that's going to break up into 2 silver ions and 1 sulfide ion, okay? Notice that this breaks up into 2 total ions on the right, and this breaks up into 3 total ions, right? 2 from here and 1 from here. So these both produce different amounts of ion, different amounts of moles of ions for every 1 mole of the ionic compound, right? Now let's set up the ice table. So initially, we got none of each, right? Now the change, check out the change. Because this is 1 to 1, it's just going to be plus x. And this is going to be 2x and x, right? Because it's 2 to 1. And now the equilibrium is going to be x and x. And over here, it's going to be 2x and x, right? We're just going to add all of these up. And just pay attention to why I'm doing this, because I'm showing you why you can't just compare KSP values to determine how soluble something is. Now we write out our KSP expressions, right, for each of these, right? This is just the same drill we've been doing before, right? KSP for this is going to be the concentration of copper 2 plus times the concentration of my sulfide 2 minus. In this case, the KSP is equal to silver plus, and it's going to be squared because the coefficient of 2 in front of the silver turns into an exponent, right? Times the concentration of my S2 minus. Great. Now let's put in our KSP values, which would be given to you, right? These are the KSP values for your ionic compounds, right? For copper sulfide, it's 8.5, 10 to the negative 45. And for silver sulfide, it's 1.6, 10 to the negative 49. So originally you might think, oh, well, this is larger than this, right? So therefore, this must be going more to the right, meaning we must be making more of the ions, which means, oh, it must be more soluble than this, right? Well, let's mathematically look and check to see if we're right on that, right? If we plug in our x for our equilibrium concentrations, notice when we solve for x here, it's going to be x equals 9.2, 10 to the negative 23. But when we solve for x here, we put in our equilibrium concentrations, right? 2x and x, and we get that this is 4x cubed, right? When we solve for x, check this out. It's 3.4, 10 to the negative 17. Now notice, I guess I had my animations off, but I'm just showing you the KSPs over here for each of these. But notice what's going on here. This x value is larger than this x value. And remember what the x value is telling you. It's the molar solubility, right? How much of these ions actually are there? How much this ionic compound dissociates and I don't even know if that's the word, solubilizes. I feel like I've used that before. I don't think that's an actual word, solubilizes. But the correct term is dissociates, which kind of means the same thing. All X is telling you is how much of this is, from a molarity standpoint, dissociating. And notice that this is larger, meaning there's more ions for this situation than this, right? Because this number is larger than this, this is dissociating way more. This ionic compound, it's telling you that you're dissociating this way more to a higher degree than this. And by how much? Look at the magnitude, right? 10 to the negative 17 versus 10 to the negative 23, right? What is that? That's order of magnitude of 6 times, right? So what this is telling you is that even though the KSPs, right? Just take a look at this. The KSPs, this is smaller. This is smaller than this. But the solubility in this case is larger here than it is here. So this is an example mathematically just showing you when an ionic compound produces a certain amount of ions, that's what's going to determine how soluble it is. It's going to affect the solubility of it and influence the solubility of an ionic compound. Okay, so realize that the silver sulfide is actually more soluble than the copper sulfide, even though the KSP for silver sulfide is smaller than the KSP for copper sulfide, right? Because the solubility is all dependent on whatever these X values are, the molar solubility. And if you go back a slide, that's really what we were talking about. I'm going to go back from my animations, but if you go back on this slide, that's what I was really talking about, right? Notice in this case, this produces 3, this produces 2 ions. They're their KSPs, but notice the solubilities. This solubility is larger than this. This solubility is larger than this, even though the KSP is smaller for magnesium hydroxide. Okay. Hopefully you guys understand now at this point. Hopefully this makes sense. You can look through this, and if at any point it gets confusing, like I said, feel free to reach out. All right, let's keep going. So we get the common ion effect. The common ion effect. So the effect of a common ion on solubility. So how does that influence the solubility? And what does a common ion even mean? We talked about this before. A common ion just basically means that if I have an ionic compound and it's trying to dissolve, right, into its respective constituent ions, right, calcium 2 plus and 2 fluoride minus. If, let's say, I add a common ion in solution, meaning I'm just adding another ion that is one of the ions that's part of the ionic compound. If I add more of it, remember what we said when we add more of something, what Le Chatelier's principle tells you is if you add more of something to the product side, the equilibrium is going to respond by shifting to the left, right, to basically balance out that equilibrium. And really what this is telling you is that if you're trying to have this dissolve and dissociate and it's trying to go to the right, you're stopping it from going to the right by adding more of one of the ions, right? Because the equilibrium gets thrown off, right? If you're trying to keep the equilibrium constant, a constant number for this dissociation, if you're going to add more of something, it's going to throw the equilibrium off. And to get the number back to a constant, you got to go backwards. Right? You have to make more of the solid to maintain equilibrium. And we can do an ice table for this and show you that if you didn't add a common ion, right, if you just had 0 and 0 of each of these, you get that the molar solubility for this, if you do the math, is 3.32 10 to the negative 4. Right? This is the KSP for calcium fluoride. So this is the molar solubility of calcium fluoride in pure water. Sorry, that shouldn't be of. In pure water. But now, what if you add 0.100 molar of a common ion? What happens then? Right? Now let's calculate the molar solubility, what this X is with a common ion present. And it's going to show you something interesting. So if you set up your ice table, now your initial concentrations are not 0 and 0. It's 0 and 0.100, right? Because you started with a certain amount of fluoride. That's the common ion. You purposely added this common ion in the solution. What happens to the molar solubility now? Right? Because that's what we're calculating. What is the molar solubility of calcium fluoride in a solution containing 0.100 molar sodium fluoride? You guys know from your solubility rules that sodium fluoride is, pretty soluble, meaning that it's going to break up completely into sodium plus and fluoride minus, right? So if you have 0.100 molar sodium fluoride, you also have 0.100 molar F minus, right? Because this completely breaks up. And this isn't a partial dissociation. So as a result of that, you actually are starting with 0.100 molar of your fluoride. And now you describe your changes, right? Plus X and plus 2X, right? Because there's a 2 in front of here. And now your equilibrium concentrations aren't X and 2X. It's X here, right? Because 0 plus X. But now in this case, it's whatever common ion amount you started with, 0.100 plus 2X. And now when I plug this into my solubility product constant expression, right, the equilibrium expression, I have 0.100 plus 2x. I can make the x a small approximation, right? Why can I do that? Because the KSP is really small relative to the amounts I'm starting with. So I'm going to make the x a small approximation and get that my x is 1.46 times 10 to the negative 8. And check this out. The molar solubility decreased as a result of a common ion, right? Check it out. The x used to be a magnitude of 10 to the negative 4, but now it's 10 to the negative 8. So what is this telling you? This is telling you that less calcium fluoride dissolved in the solution because you had a common ion already present in the solution. And remember, according to Le Chatelier's principle, based on that principle, if you're adding a common ion, it's going to shift the equilibrium to the left, forcing more formation of the solid, which is then in turn decreasing the amount of this that's going to go towards the right. So you're not dissolving this as much as you used to when it was in pure water, right? When you just had pure water and no common ion present, none of it present at all, it just dissociated to the extent that it could normally if it was in pure water. But now that you added a common ion, you've disturbed the equilibrium. You're pushing it towards the left. You're forcing the formation of solid, and you're preventing the solid from even breaking up further into its positive and negative constituents. So your molar solubility is going to decrease now because it's going to the left as a result of a common ion. So that's the big take-home message here, right? Is whenever you have a common ion present in a solution that you're trying to dissolve an ionic compound, you have a common ion in there, it's going to drive the equilibrium to the left, which means it's going to decrease the molar solubility as a result of that common ion, okay? Hopefully that makes sense. Let's keep going here. So what's the effect of pH on solubility? Well, if your pH is high, check this out. If your pH is high, that means it's more basic, right? And more basic means you have more OH minus floating around in your solution. And if you're trying to dissolve an ionic compound that has an OH in it, right? In this case, you have magnesium hydroxide breaking up into magnesium 2 plus and 2 hydroxide ions. If you're adding more OH minus, right? In this case, it's also a common ion, right? You're adding OH minus, you're adding more base, you're making the pH higher. What is that going to do? It's going to also shift the equilibrium towards the left, right? Because you're adding more products, so it's going to force its way towards the reactants to balance out that addition and maintain equilibrium. And now you're decreasing your molar solubility as a result of increasing your pH here, right? If your pH is low, right, that means you're more acidic, right? So what that means is you're adding more H3O plus, uh, or H plus, right? If you're adding more of that, what's going to happen? Well, if you have OH minus in your solution and you have H plus floating around, what does H plus do with OH minus? It makes water, right? So H3O is going to react with OH, or whatever you want to say, whatever you want to call it, H plus reacting with OH minus, whatever. Bottom line is now what's happening is you're decreasing the amount of OH minus that's in your solution. And if you're decreasing the amount of product, what does Le Chatelier's principle tell you it wants to do? If you're decreasing products, you want to shift the equilibrium towards the right to replenish whatever product you lost, right? More of this solid is going to want to dissolve because you're depleting this as a result of adding more acid. So bottom line is if you're decreasing your pH or making your solution more acidic, you're driving the equilibrium to the right to dissolve this even more than it normally would if you maintain the pH. And what is the result? That you've now increased the solubility of your magnesium hydroxide. So all this slide is telling you is that you can affect the solubility of an ionic compound by changing the pH, right? If you add more base, what's going to happen? If you add more acid, what's going to happen? Right? In this case, and I made a note here, in general, solubility of an ionic compound containing a basic anion, right? In this case, it was OH minus, but what if you have other basic anions like S2 minus or CO32 minus? These are also basic anions, and they're the most common ones that you'll see. There's really not that much variability of being exposed to basic anions, but if you notice you have a basic anion, the solubility of an ionic compound containing a basic anion is going to increase with increasing acidity, right, or decreasing pH, and we just saw that. Right? So pH can also have an effect on solubility. That's really the take-home message here. All right, here's a practice problem. It says determine whether each compound is more soluble in an acidic solution than it is in a neutral solution, right, or just pure water. So how do we figure this out? If I look at something like barium fluoride, you guys remember how we figure out whether an anion is acidic or basic or neutral, right? So we look at F minus, and how do we figure out if F minus is basic? If an anion is basic, remember we said anions could be either basic or neutral. And the way we find that out is we're like, okay, F minus, if it pairs up with an H, right, we have HF, right? HF is a weak acid. It's not one of your strong acids. So if you have a weak conjugate acid, if you have a weak acid of a conjugate base, then what does that mean for the F minus? That means it's going to be a weak base, right? The F minus is going to be a weak base. So if it's going to be a weak base and you're trying to add acid to your solution, remember what this question's asking you. It's saying determine whether each compound is more soluble in an acidic solution. So what that means is if you're adding H plus to this, you have a weak base floating around. So what that means is if you add acid, it's going to eat up the weak base, and it's going to drive the equilibrium towards the right. It's going to force this solid to dissolve even more because you're eating up the F minus by adding acid. So you're increasing the solubility of barium fluoride as a result of adding acid. All right, what about part B, silver iodide? So silver iodide, if you look at that, again, look at the anion, right? You have I minus. So if you pair that up with an H, it's going to form HI, right? HI is a strong acid. It's one of your 6 strong acids. So what does that tell you? That tells you that the I minus does not want to behave as a base because it doesn't want to make HI. Remember, strong acids like HI want to break up into H plus and I minus, and they have no interest of coming back together. So I minus does not want to make HI. It just wants to stay H plus and I minus. So I minus is not going to do anything. It's just going to be a neutral anion. So it's not going to be basic. So if you add acid to this solution of silver containing silver iodide, if the I minus isn't going to grab that H from this acidic addition, and I minus is just gonna want to hang around on its own and not do anything, then your solubility of silver iodide is not going to be affected, right? You're not driving the equilibrium more towards the right or towards the left because I minus is just hanging around, not doing anything. It's just a neutral anion. Okay, so in the case for B, silver iodide, the solubility is not affected based on the addition of acid. What about calcium hydroxide? Well, this is a little more obvious because you guys know that calcium hydroxide, when it breaks up, is going to break up into calcium and hydroxide. And if you add acid to hydroxide, what's going to happen? The acid's going to eat up the hydroxide, right, which is a base. And that means you're depleting the hydroxide that broke up. And if you're depleting the hydroxide that broke up, the solid calcium hydroxide is just going to want to naturally dissolve more to replenish the hydroxide that got eaten up by the acidic solution, right? So what does that mean? The solubility of this solid is going to increase, right? It's going to want to break up even more. Hopefully that makes sense, and I think that, well, I guess I didn't give you guys any practice problems for this, but hopefully conceptually this makes sense, and maybe you'll see other examples related in your ACS guide where they might ask you something about this, and you can practice these concepts on your own. All right, so let's talk about precipitation equilibrium. All right, so we're almost done. I know we're 50 minutes in about so far. We're going to wrap up with a couple more concepts, one of them being precipitation equilibrium. So what is precipitation equilibrium? So you guys remember back from Gen Chem 1 that if you have two compounds, right, let's say A and B, and another compound that has components C and D, you guys know that if you do a double replacement reaction, you're going to mix A and D with C and B, right? Because A is positive, B is negative, C is positive, D is negative, right? Plus and minus meet together. So what's going to happen is the plus from one compound, which is A, is going to mix with a minus of another compound. In this case, it's D. So you got A and D. And you have the positive of another compound, which is C in this case, and the negative of the other, B in this case, and you got C and B, right? So it's just a double replacement reaction, right? Now, you guys know that when you do this, though, imagine these are both soluble in water, right? Imagine these are both in water, and these both break up into A, B, C, and D, right? These ionic compounds break up. But imagine that when they break up and then they reform to make new products, one of them is going to precipitate out, right? And the other one might not. But the question is, does precipitation actually happen? Right? That's what we need to look at, because from your solubility rules, you guys know that you can look and be like, oh yeah, when two ions are paired together, are they gonna, if they form a solid, are they gonna stay a solid or are they not gonna stay a solid, right? But now we can mathematically figure out if a precipitation actually happens, because it could be that there's not enough ions in the solution to form a solid. Or what could happen is that there might be way too many ions, and it'll definitely form a solid, and you're gonna have a pretty saturated solution of this solid compound. So we need to look at what criteria is going to help us determine that. Imagine I have an example, or a scenario if you will, of a solution that is prepared by mixing X molar of lead nitrate, right? That's just your one ionic compound. And imagine I got some X molarity, some concentration of sodium bromide. You guys know from the solubility rules that these are both soluble, right? They're going to break up into their respective ions and their constituent ions. Will there be any precipitate formed? Well, let's take a look. So notice I matched the color coding here for you guys to understand what's going on. Here's your lead nitrate and your sodium bromide, and you balance this equation. You do a double displacement, and then you get lead bromide and silver nitrate, and there's a coefficient of 2 in front of these. So let's do something where you've seen this before. What happens when you have an ionic equation? You can write the complete ionic equation. You guys remember that? This is all going back to Gen Chem 1, right? So taking an ionic compound mixture and showing how, the ionic compounds break up into their ions. And here it is, right? These are both soluble, so they're going to break up. And then lead bromide is actually supposed to be a solid. If you look at your solubility rules, lead bromide should not be soluble, right? So it's just going to stay that way. And then you have your sodium nitrate breaking up into their ions. Guys, if you do not know how to do this, this is going to be a problem, because you need to be able to know how to write ionic, complete ionic, and net ionic equations to be able to solve a problem like this. Here's the net ionic equation. Remember how you get a net ionic equation? You basically cancel the ions that are the same on the left as they are on the right. And you notice that the ones that are the same are sodium and nitrate, right? They cancel out. And the only thing you're left with is lead 2 plus and 2 Br minus makes lead bromide. You guys need to be able to know how to do this, okay? Make sure you know how to do this, because like I said, if you can't do this, you'll see how you might get your answer incorrect. Now, why did we do all of this? Because we know that now we can write a KSP for this, right? The KSP of this solid dissociation is going to be equal to the concentration of lead times the concentration of Br minus squared, right? But now we're going to introduce a new concept here, Q. And it's not really a new concept, because you guys remember what Q is relative to K, right? Expression-wise, K and Q look exactly the same, right? But KSP is telling you something different than Q. You guys remember that Q is telling you the position of where you are relative to equilibrium, right? So you could be at any point in equilibrium. You're not at equilibrium when you're talking about Q, right? Q is just where you are at a particular point before equilibrium is reached. Right? So bottom line is, what I'm saying here is you can have more of one of these or less of another, and it won't be KSP, right? It won't be equal to K. It won't be at equilibrium, right? To be at equilibrium, you have to have a certain exact constant concentration of these to get KSP, right? KSP is a constant. So you need to figure out where you are relative to equilibrium, right? Remember that if Q is less than K, what does that mean? Well, let's think about this when we learned about it before. When Q is less than KSP, what that tells you is that you have less products than what you would have if you were at equilibrium, right? Remember that equilibrium is products divided by reactants. And if Q is less than K, what that tells you is that your denominator, your reactants, is larger than your numerator, which is products, right? Products is numerator, reactants is denominator, right? Products over reactants. So if Q is less than K, what that's telling you is that you have more reactants than products and you're not at equilibrium. So you need to drive the process forward. So what that's telling you is you don't form a precipitate. You're unsaturated. How does that make sense? If Q is less than K, you have no precipitate. Well, think about it. If you're not at equilibrium, what that means is, you have less products than you do reactants when Q is less than K, right? The reactants is more prominent. But if you want to get to equilibrium, you need to drive the process forward to make more products. And the products in this case are the ions, right? Not the solid. The solid is the reactant, right? I know this looks weird because this looks like a product over here, right? But in reality, you guys know that, you know, if you want to go this way, this is what's really happening. I know this is flipped. I know right now this looks like a product and not a reactant. But you guys know that when you're talking about the dissolution of an ionic compound, when you describe how an ionic compound dissolves, we're talking about the solid, aka the reactants, right, is breaking up into its ions. Even though this is written in the reverse way, you guys understand that this is basically your quote unquote reactants and this is your products. Your products are always going to be the ions, the concentration of the ions, right? So what I'm really trying to get at here is if Q is less than KSP, you're trying to drive the formation of ions, right? The products. And therefore you won't form a precipitate. You won't form a solid when Q is less than KSP because you're trying to convert more of the solid to the ions, which means you're going to have ions and not solids. So no precipitate forms when Q is less than KSP. What happens when Q is equal to KSP though? Now we're at equilibrium, which tells you that now you have very little precipitate, very little solid. You guys know that precipitate just means solid, right? So when Q is equal to KSP, what that's telling you is that now you're at equilibrium, and the only way you form any solid or have any solid is because of the value of K, right? The value of KSP. You guys know that if KSP usually is a small number, but that small number is telling you how much, or really just how little, because KSP is always such a small number, it's telling you how little amount of your solid is actually breaking up into your ions. We just talked about this. So when Q is equal to KSP, you have very little solid because at that point, you're just at equilibrium. Now, if Q is greater than KSP, what does that tell you? That tells you you have way too many ions floating around, right? And you're way off the equilibrium. So if you have way too many, if this is way too high of concentration spontaneously, if K wants to stay constant, if you want to maintain equilibrium, if you have too many ions, it's going to drive the formation of more solid, right? To maintain equilibrium, you need to make sure that to keep K constant, this has to be certain concentrations. So you're driving the formation of solid, which means precipitate definitely forms when Q is greater than KSP. Okay? Hopefully that makes sense. If that's confusing, like I said, reach out to me, let me know, ask questions, okay? Okay, let's do a practice problem. Because here's the thing, in my example over here, we didn't tell you what, how much of each of these you have. So you can't even calculate Q, right? If you actually had these, if this wasn't just X and X, if I actually gave you the numbers for these, right, the concentrations of each of these, you can calculate Q, right? Figure out where you are in equilibrium. And then once you know what Q is, you can compare it to KSP. And you can say, okay, well, is Q greater than KSP? Is it less than KSP? Is it equal to KSP? What's my situation? Where am I in my solution? And depending on where I am, how much of this stuff I have is going to tell me if I'm going to form precipitate, solid, or if I'm not going to. Right? It all depends on Q relative to KSP. So let's do a practice problem, right? Let me read the problem. It says a solution is prepared by mixing 150 milliliters of a 1.00 times 10 to the negative 2 molar magnesium nitrate, and you got 250 milliliters of a 1.00 10 to the negative 1 molar sodium fluoride. Right away, just reading from this problem, you already know from your solubility rules, which, by the way, you do need to memorize your solubility rules, right? We made you memorize this in Gen Chem 1. You should still remember it from Gen Chem 2. So for whatever reason you forgot, please memorize that because you at least need to know which compounds are soluble and which ones are insoluble, but we know that it's not really insoluble, right? It's partially soluble. Some of it will dissolve, just depends on how much, aka what the KSP is and the solubility, molar solubility is. We looked at all of that before, but make sure you know your solubility rules. Bottom line is that now you know if you know your solubility rules, you know magnesium nitrate is soluble and sodium fluoride is also soluble, and you have a certain concentration of these and a volume. Does it precipitate form? Okay, so what does that tell you? That tells you you're like, okay, I need to calculate Q and compare it to KSP. And they gave you the KSP for magnesium fluoride. Okay, so they basically told you what the solid is. And that's great, because when you're trying to write this equation out, you know that one of the products is going to be magnesium fluoride. So they already gave you a hint on that. The question is, what is the other product? Well, if you write this out, magnesium nitrates, MgNO32 plus NaF, what does that make? You want to balance the equation, right? Make sure you're balanced. And you write your complete ionic equation, right? So anything that's aqueous that dissolves is going to break up into its ions, right? And remember, this is solid, so that stays that way. And you cancel the common ions, right, on the left and the right, and you get your net ionic equation, which is just showing you the dissolution of magnesium fluoride, MgF2 in solution. So now you can write your expression Q equals, just like KSP, Q equals the concentration of magnesium times the concentration of my F minus squared, because there's a 2 in front of there, right? You guys want to make sure that you know that there's a 2 there. You wouldn't know there's a 2 there if you didn't balance this correctly, right? You need to make sure you balance this equation correctly to be able to get the right coefficient so that you get the right expression for Q or in KSP, right? This exponent is influenced by balancing the equation correctly. That's why I'm trying to tell you guys that you need to remember to know how to write an ionic equation, a complete ionic equation, and a net ionic equation. Make sure you get that down, because that's all going to influence your answers going forward. Now we can calculate Q, but here's the thing. We can't just plug these molarities in over here, because we have certain volumes that we need to consider, right? Whenever you're given a volume and a concentration together, you realize that when you're preparing a solution, the concentration is influenced on the volume of each of these, right? Right? It's 150 milliliters plus 250 milliliters. So however amount of magnesium, let's say, you're trying to calculate that you have to divide it by the total volume, right? And notice I show this work over here, right? So if I have 150 milliliters of my magnesium ion over here based on my net ionic equation, I can just calculate the amount of moles of magnesium I have from my volume, right? Knowing the concentration, right? Where is this coming from? Right over here. Right over here, we're just converting to liters. That's easy. But now we need to know how many moles of magnesium you have. That's all based on the concentration, which is right over here, right? So we've done this stuff, this kind of calculation before for titrations, right? We calculated the amount of moles we have, and then we divide by the total volume, right? Pretty similar stuff. So you're going to take this and divide it by the total volume to get your concentration of magnesium 2+ in your solution. Same situation where you're trying to calculate the concentration of your F minus, right? You have 250 milliliters of it, convert to liters, and now multiply by the concentration of it right over here to get the moles of F minus in there. Okay, you got your moles of F minus divided by liters to get concentration, molarity, divide by the total volume, just like we did over here, and you get 0.0625 molar F minus. Now we can plug these into our Q. And when we plug it into Q, what do we get? We do this math on our calculator, we get 1.46 10 to the negative 5. What is that relative to KSP? Looks like it's bigger, right? Q is greater than KSP. So if Q is greater than KSP, a precipitate forms, right? Because now when Q is greater than KSP, what that means is you have way too many ions, way too many products, right? Just like I said in the last slide, if you have way too many ions floating around and you're trying to maintain equilibrium, it's just going to drive the process to the left, formation of solid, precipitate. And now you've just shown mathematically by comparing Q and KSP that a precipitate forms in this particular case. Okay? So now, what if we want to know more about this problem? So now we know a precipitate forms. What if we want to know the concentrations of each of these ions in the solution? And the question is, which ion do we have more in excess, right? That's really what we need to see. And I just showed you how to do this calculation, right? You're figuring out the moles of each of the ions you even have to start with, right? This is from the previous slide, these calculations. Right? This is just telling you the amount of each ion you have in the solution. Now, the question is, how much of this stuff is going to become solid, right? Because Q is greater than KSP. So that means you're definitely forming solid. And if you're forming solid, how much ions are going to be left over, right? So the only way to know that is to draw a reaction table for this, right? Like, you realize before the reaction, you have just each amounts of these, right? But if I'm forcing these ions to become a solid because Q is greater than KSP, what's going to happen is all of the magnesium that you have available, all the magnesium 2+, is going to get consumed and form into solid with fluoride. And why is this going to get consumed? Because you check this out, you have more F- than you do magnesium, right? So what's going to happen is when you have the quote-unquote reaction where these ions become a solid, I mean, it is a reaction, right? You're turning ions into a solid. That's a reaction. I shouldn't say quote-unquote, but really you guys understand that because you have magnesium ions floating around, you're now going to convert all of the magnesium ions into MgF2. So you're driving this process forward. And now you have, after the reaction, you have 0 magnesium left, and all of that paired up with as many F- as it could, and particularly this amount of moles of F-. But keep in mind that there's a coefficient of 2. So for every 1 mole of these, it's got to pair up with 2 moles of F-, and there we show it, right? It's going to be 2 times the amount of magnesium that you have. So now we see that the amount of F- that we have left is 0.0220. So this is the amount of F- that is basically floating around in excess, right? Because we paired up as much F- as we could with Mg. Whatever Mg was available, whatever amount of magnesium was available to make the solid, we took that amount out of our current stock of F-, and we figured out how much F- is left after making magnesium fluoride. Okay. Now, what happens? Well, we have no magnesium 2+ left. It all became this, and we have this left over. So now we can calculate the concentration of F- that's left. And we just divide that by the total volume. Remember, the volume from the previous problem was just 150 plus 250 milliliters and convert to liters. There it is. And now the concentration of your F- that's left over is going to be this. Now that's great that we know how much F- is left. But we know in reality that magnesium fluoride solid is still going to form some magnesium ion, right? It's not really 0, because we know that if we look at and do an ice table, we know some of this is becoming this, right? Very little of it, but at least some of it will. And we know that because of the KSP, right? The question is how much. We need to draw an ice table, but we know we have a common ion, right? We have a common ion already present in our solution, right? We have F- in excess, and that's going to drive the equilibrium to shift towards the left. So it's not like this is going to solubilize as much as if it was in pure water, because we have a common ion, right? This common ion is going to influence the solubility of magnesium fluoride, but nonetheless, some magnesium will be in the solution. And the question is how much? Well, we can draw an ice table for that. So we have initially 0 magnesium, quote unquote, right? Based off of this, we have 0. We have 0.0550 molar F minus. That's an excess. We just calculated that from here. What's the change? It's going to be plus X and then plus 2X, right? And their equilibrium is going to be X and then 0.0550 plus 2X. And now we plug this into our KSP expression. And we realize that now, and we were given the KSP. I think it was given in the previous problem, in the problem, yes, it was given. 6.4, 10 to the negative 9, there it is, equals X, right, concentration of magnesium in equilibrium times the fluoride concentration at equilibrium squared. We can make the X a small approximation, right, so we don't have to do the quadratic or anything like that. We're allowed to make this approximation because this is a really small KSP, and you can check with the 5% rule once you get X. Here's X. If you divide that number by, what you added and multiply by 100, you're definitely going to be below 5%. So we're fine to make that approximation. But bottom line now is that this is your magnesium concentration. We just solved for X, which is our magnesium concentration. So now we know our concentrations of each of these ions in solution. So sometimes bottom line is we don't always want to know if we form a precipitate, right? We know now we form a precipitate because Q was greater than KSP. But now we know that, now we want to figure out, okay, what is the concentration of each of the ions in our solution? And we were able to figure that out. But just to recap, how did we figure that out? First, we drove the reaction to completion. We drove, the amount of ions that actually would form solid magnesium fluoride, and we saw which ion was left over in excess. And then we figured out how much of this goes back to magnesium 2+, knowing that some of this is going to dissolve based on the KSP, but keeping into account that there's a common ion floating around, and that's going to influence the solubility of it. And remember what we said, when we have a common ion in solution, what is it going to do? It's going to decrease the solubility. It's going to shift the equilibrium to the left, right, in favor of the formation of the solid. And then we can set up an ice table and figure out, okay, how much magnesium 2+ dissolved? It's going to be less than if it would be in pure water, but now we have a common ion. So this is the amount. All right, just to recap what we just did. All right, what about selective precipitation? So with selective precipitation, you guys realize that if you have two ions that are floating around, right, barium 2+ and silver plus, if I expose these two positively charged ions with an anion like chloride, which one is going to precipitate first, right? Because if you know your solubility rules, you guys know that silver chloride is not soluble, but barium chloride is. So it actually doesn't even matter how much chloride you add, because at some point, well, that's not actually true. At some point, if you add enough chloride, you can precipitate both. But bottom line is that if you add chloride to this solution, the first thing that's going to precipitate is the silver chloride, not the barium chloride. Okay? And we can actually figure out mathematically, which of these ions, when they're exposed to an anion, which one's going to precipitate out first. This is called selective precipitation. This is actually really valuable because if you have certain contaminants in like water, right, like certain ions you don't want in water, you can selectively precipitate the ions you don't want in the water and keep the ions you want in the water, right? Any healthy ions or minerals and things like that, you can keep the good ones and take out the bad ones, right? That's just one application of selective precipitation. But here's a practice problem related to it. So it says a solution contains 1.00 10 to the negative 4 molar of copper plus and 2.0 times 10 to the negative 3 molar lead 2 plus. And if I was thinking about, copper and lead and water, I don't think I'd want either one of these, but I definitely don't want lead in my water, right? So maybe we can selectively precipitate this out. It says if a source of I minus is added gradually to the solution, will PbI2, which has its KSP, or copper iodide, which has its own KSP, precipitate first? So bottom line is what this is saying is if I gradually add I minus to the solution, which is going to precipitate first? And right away, you can look at the KSPs and you can probably get an idea of which one will precipitate first. Notice that the copper iodide, has a lower KSP. But remember what we said, we can't really look at KSPs like relatively and confirm that, because notice with copper iodide, it forms copper and iodide, that's 2 ions. But in this case, lead I2 forms 3 ions, right? Pb, which is lead, that's 1 ion, and then 2 I minuses, right? So lead and 2 I minuses, that's 3 ions total. And remember what we said, that we can't compare KSPs and definitively say which one ends up being more soluble or which one's going to form a precipitate first if the amount of ions are different. The amount of ions formed as a result of the dissociation are different. So they're asking which precipitates first, and they then said specify the concentration of I minus necessary to begin the precipitation of each of these salts. Okay. So you're probably thinking like, wow, what a confusing problem. It's not really bad, right? Because here's the thing. They gave you the KSP, right? They told you how much of the ions you have. And all they're asking is how much I minus do you need to keep to get each of these to start precipitating out? Well, if you write the KSP for this, for each of them, KSP is equal to Pb2 plus I minus 2, right? Because there's 2 I's. And then for the copper iodide, it's KSP equals copper plus times the concentration of I minus. You plug in your KSPs that was given in the problem. You also plug in the concentrations of your ions, right? It said that lead, you have this amount, so I'm plugging that in here. They gave you the amount of copper in molarity, and you plug it in over here. And check this out. You solve for I minus in this case. That's the only variable that's left here. And what you'll notice is when you solve for I minus, which one's smaller? It looks like this one's smaller, right, than this. So what is this telling you? That means you need this amount of I minus to start precipitating the copper iodide, right? And you need less of the I minus relative to this. You need more I minus relative to this to start precipitating the lead I2, right? So bottom line is because you need less iodide than to precipitate this than this, what that's telling you is that the copper iodide will precipitate out first. Okay. It's pretty much the gist of that. Pretty simple problem, guys. It's not too complicated. Big picture is you're just trying to figure out how much I minus you need to start precipitating each of these out. And it turns out that you need less I minus to start precipitating copper iodide than you do lead iodide. Okay, we're going to wrap this up with some assessment questions. So this might be an ACS style question, right? It's going to say a solution contains equal concentrations of these ions. When potassium carbonate is added to the solution, which cation precipitates first? So which of these cations are going to precipitate when you expose them to carbonate, which is the anion? The potassium doesn't even really matter because potassium carbonate, if you know your solubility rules, is soluble, which means you're going to form K plus and CO3 minus. And what I would do is I would just look at the KSPs, right? Let's look at our table. And, they would give you this on the ACS. They're not going to give you the whole table, but they'll only give you the stuff you need to solve the problem. But let's just find calcium carbonate over here. There it is. If calcium's paired up with carbonate, this is the KSP. If iron is paired up with carbonate, this is the KSP, right? Notice the magnitudes. What we're really paying attention to are the order of magnitude. This is 10 to the negative 9. This is 10 to the negative 11. What about magnesium carbonate? Well, magnesium carbonate's over here. That's going to be 6.82, 10 to the negative 6, okay? So which one's larger? Remember, the larger KSP means higher solubility, but that's only true if the ionic compounds you're comparing produce the same number of ions. In this case, each of them produce the same number of ions, right? Calcium carbonate, 2 ions. Iron carbonate, 2 ions. Magnesium carbonate, 2 ions, right? We can compare the KSPs now because they produce the same amount. And the larger the KSP, the more soluble it is, right? The more ions you have, concentration-wise. So it turns out that, you don't need much carbonate to precipitate out the iron, because the iron has the lowest KSP, right? A lower KSP means that your stuff is less soluble. So if I'm adding carbonate to a solution of calcium, iron, and magnesium, the iron's going to precipitate out first because it doesn't take that much carbonate to precipitate it out, given that it has such a low KSP relative to the other ones, right? Looks like this one's the lowest, right? 10 to the negative 11 versus 10 to the negative 9 versus 10 to the negative 6. So the answer is iron carbonate, okay? Now what's going to precipitate out next? If I keep adding carbonate, the next one's going to be calcium carbonate, followed by magnesium carbonate, right? Think about it. Because the magnesium carbonate KSP is so large, what that's telling you is that you're allowed to afford to have more carbonate ion in your solution, right? The solubility of the carbonate is going to go up because the KSP is larger, right? So if I'm adding carbonate, I can afford to add more carbonate without precipitating magnesium, but I can't add as much carbonate for the other ions before they precipitate. Okay. All right. Pretty much this is the last slide. So this question I'm not going to go over. I want you to give that a shot. This question is exactly like the one we did last time. So we just saw if a precipitate forms. What do you need to do for this problem? You need to compare Q and KSP, right? So get the Q, compare it to the given KSP and see where you're at. If Q is greater than KSP, you have a precipitate form. If the Q is equal to KSP, you have very little precipitate, right? And then if Q is less than KSP, then you don't have any precipitate form. And we talked about why and all of that in the previous slide. So this problem is just like that. So give that a shot. That basically concludes objective 14, solubility equilibrium, okay? So like I said, if you have any questions, please feel free to reach out by email or, in person if I'm in my office or something like that, okay?